All right, this is the last section of the chapter. We're talking about exponential and logarithmic rules. You're going to learn 4 rules today, but before we go over those 4 rules, we have to be able to evaluate this limit, and we have to be able to do this part over here. So I'm going to show you that limit right now. This is not the only way that you can do this. I'll show you a different way that you might find easier, but this way is going to prove what this limit value is, hands down. So the limit as h approaches 0 of e to the h minus 1 over h. Before I start doing this, I do have to tell you that there is a definition of e, that the limit as h approaches 0 of 1 plus h to the power of 1 over h is equal to e. That's just the definition. If you were in my room, I would be able to point over above my door over here that I actually have that hanging up there because I love the number e. But when I look at this definition right over here, I can now sub that into this limit. So that since I'm talking about the limit as h approaches 0, instead of e to the h, I actually have this expression to the h power. So what I can look at that as is 1 plus h to the 1 over h power. Instead of writing e, I write all that to the h power minus 1 all over h. Now I look at the 1 over h power to the h power. Those cancel each other off. And now I have the limit as h approaches 0 of 1 plus h minus 1 all over h. Now I see 1 minus 1 up there. This becomes the limit as h approaches 0 of h over h, which really h divided by h is just 1, right? So that's one way to find this limit. The other way that we can do this is by using our calculator. Remember last chapter we talked about using the calculator to evaluate limits. I can pull up my calculator right here, and in my y equals menu, clear some stuff out here. And instead of putting, I want to now put in this expression right here, the e to the h minus 1 all over h. So I put in e to the h minus 1 all over h. And remember, in this problem, we are looking for limit as h approaches 0. So essentially, I'm looking for, on this graph, what is the y-intercept. And I can see that it makes sense that the y-intercept looks like it's at 1. Although if I graph it, I can actually see that the value of y is undefined there. But as I move to the left and the right, I can see the limit exists. So that limit value is 1. Do you have to know the algebraic way of doing it? Absolutely not. Do you have to know that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1? Yes, yes you do. That will come in handy a little bit later. Now looking down here, a to the x is equal to e to the x ln of a. In order to do this, I usually start with e to the x ln of a. So e to the x ln of a. And we happen to know that we have a power property for logarithms. We can take this x and make it the exponent of a. So this becomes e to the ln of a to the x. We now have e to the ln. Those cancel off, and we're just left with a to the x. Are you going to need to know that today? Yes. Yes, you will. So let's move forward. Oh, there's the proof. That's a fun proof. And section 3.9, derivatives of exponential and logarithmic functions. I told you before that we don't have to use the limit definition of a derivative, but whatever. We are going to use the limit definition of a derivative to find out what the derivative of e to the x is. So I'm just pulling out from section 3.1 right now, the limit definition of a derivative, the limit as h approaches 0 of f of x plus h minus f of x over h. Our f of x here is e to the x, so I've got limit as h approaches 0 of e to the x plus h minus e to the x over h. in order to find out the derivative of e to the x, I can now rewrite this as the limit as h approaches 0 of e to the x times e to the h minus e to the x over h. Now notice how I've got a factor of e to the x in the numerator twice here? I can actually factor that out. I can rewrite this as the limit as h approaches 0 of e to the x times the quantity of e to the h minus 1 over h. Now here's a little trick. Because x is not the value that the variable that I'm limiting here, it's just some other variable. I actually have e to the x can behave like a constant. So I can take that constant and using limit properties, I can pull it out of the limit. So this becomes e to the x times the limit as h approaches 0 of e to the h minus 1 over h, which we just proved limit as h approaches 0 of e to the h minus 1 over h, that's just 1. So the derivative of e to the x is e to the x times 1. Here's your first gift for today. This is a huge, huge, huge realization. That, drum roll, the derivative of e to the x is equal to e to the x. To me, this is possibly the easiest derivative to calculate. Anytime you see derivative of e to the x, the answer is e to the x. Of course, we do have to take into account the chain rule. So if you have in e to the x any sort of input into the x, you have to multiply by the derivative of the input. But that's not too hard, and we'll go over that today. So let's see here. Oh, there we go. Now the derivative of a to the x, in the do now, we showed that a to the x was equal to e to the x ln of a. So now here, I can call this the derivative of e to the x ln of a. Remember, in the first part of the video, I did show you that e to the x ln of a is the same thing as a to the x. So now I can just use the rule from the previous page to figure out what the derivative of e to the x ln of a is. And the derivative of e to the x ln of a is going to be e to the x ln of a times the derivative of the input. So here, since my input is something other than just x, I've got to multiply by the chain. Remember, we worked on that a few days ago, and we kept saying the chain is the most common thing for people to forget. So I just got to multiply by the derivative of x ln of a. Now this part looks difficult because we don't know what the derivative of ln is yet. However, we do know the derivative of a linear function. Since a here is just any number, the derivative of x ln of a is just ln of a. So the derivative here becomes e to the x ln of a times ln of a. Or we can actually change this back. It becomes a to the x ln of a. So there's your second rule for today. You now know how to find the derivative of any exponential function. The derivative of any exponential function, where we have the variable in the exponent. You follow these two rules. All right? I think I have a couple of examples here for you, just so you can see. There's the chain. All right, cool. So we've got these four problems. Sorry, I can't count right now. Maybe pause, try a couple of them. Sorry about that. I wanted to spread them out a little bit so that I had a little bit more room to write here. So let's just start with this one right here. The derivative of y equals e to the 2x cubed. So in order to find this derivative, all I have to do is remember the derivative rule for e to the something. And the derivative of e to the something is the exact same thing. E to the whatever it is times the derivative of the input. So you can see I'm being very deliberate here to try to show you that I'm taking the derivative of the input to emphasize the chain here. So here, I just have to really take the derivative of 2x cubed. Derivative of 2x cubed, I bring 3 down. 2 times 3 is 6. Take 1 away from 3, I get 6x squared. So this answer, I'm just going to put that 6x squared out in front of e to the 2x cubed. I've got 6x squared times e to the 2x cubed. And now I'm done. Again, the big important thing here is to recognize the chain. Now look up here, you can see that we have a chain. I think we actually have 2 chains in this problem. This one, I've got y prime is equal to, well, I've got an e to the, so I'm going to make it e to the exact same thing. Times the derivative of that same thing that I had. That 4x cubed plus 5 squared. Now what I could do from here, I could square that binomial and then try to take the derivative of the expanded form. But really, I think using the chain rule is going to be a little bit easier. So I can see this is going to be e to the 4x cubed plus 5 squared times, now I'm doing that outside in strategy. The squared is the next outsidest function. So I'm going to have times 2 times the quantity of the stuff. And 2 minus 1 gives me 1. Now this stuff was not just x, so I now have to multiply by the derivative of the stuff. So 4 times 3, 12x squared plus 5. And I could leave it like that if I really want to. Or I could shift all of the polynomials out front. Down here, it looks slightly different, just in that instead of e, we have a 4. The only thing that changes when your base is something that is not e, y prime is going to be equal to the exact same thing, 4 to the 4x to the 4th times ln of whatever the base was. The base here was 4, so it's 4 to the 4x to the 4th times ln of 4 times the derivative of the inside. And again, if I was doing this on my own paper, I probably wouldn't put this step where I acknowledge taking the derivative of, where I acknowledge the chain. I probably would just do that all in one step. I mean, here, I bring my 4 down. I've got 16x cubed. So I'm going to have 16x cubed times 4 to the 4x to the 4th ln of 4. There, I'm done. Versus this one, now pretty similar. I don't know why I used a 4 again. Exponential, since I've got x in my exponent, I should have 4 to the negative 5x cubed ln of the base times the derivative of the chain. So times, bring the 3 down, I would have negative 15x squared. Ideally, I'd put that negative 15x squared all the way out front. So y prime is going to be equal to negative 15x squared times 4 to the negative 5x to the cubed ln of 4. All right, so not overly difficult, hopefully. Again, I think this is one of the easiest rules, but can be confusing sometimes. All right, let's move on. Check to see if I got the right answers, and I did. Now, at what point on the graph the function y equals 2 to the teeth minus 3 have a slope of 21? Whew, that looks difficult, doesn't it? All right, so I know slope indicates I need to be dealing with derivative. So this is basically saying where's y prime equal to 21? So I've got y prime is equal to, let's just take the derivative. Y prime is equal to, so I've got 2 to the teeth, derivative of 2 to the teeth is going to be 2 to the teeth times ln of the base minus the derivative of 3, so minus 0. So this question, when does this slope equal 21? So when does it equal 21? Now I just have to solve this for t. Well, I mean, looking at this, I can divide this by ln of 2. I've got 2 to the teeth is equal to 21 over ln of 2. And now I could, let's see, ln both sides. I now have t ln of 2 is equal to ln of 21 over ln of 2. Dividing by ln of 2 again, I have the answer to this question of at what point on the graph does this function have a slope of 21, would be at t is equal to ln of 21 over ln of 2 all over ln of 2. Again, the ultimate idea behind this particular problem is seeing anytime when do we have a slope of this value, slope, derivative. We need to have those two being associated with each other. Of course, I think I plugged this into a calculator. I can actually see ln of 21 over ln of 2 divided by ln of 2 is approximately 4.921. Now, we did acknowledge this section was called exponential and logarithmic derivatives. We now need to find the derivative of ln of x. And finding the derivative of ln of x, let's just look at this as y equals ln of x. We're going to use the implicit differentiation, the strategy we used from the inverse function, the inverse trig functions from last section. So looking here, I can see that I have e to the y is equal to x is actually the definition of y equals ln of x. So now when I look at this, I can recognize that the derivative of e to the y is going to be equal to the derivative of x, all with respect to x. Now looking at this, the derivative of e to the y is just going to be e to the y times the derivative of y with respect to x. Again, going back to that implicit differentiation, the chain here is equal to the derivative of x with respect to x is 1. Solving this for dy dx, we're going to divide by e to the y. We end up with dy dx is equal to 1 over e to the y, which really we know e to the y is equal to x. So the derivative with respect to x is 1 over x. Brand new rule that we have, d dx of ln of x is equal to 1 over x. And of course, we would have to acknowledge the chain if that situation were to arise. There's your third rule for today. There it is in a yellow box if you prefer that format a little bit better. And now we have one last rule for the entire chapter. The only rule that we have left. What we want to figure out is what is the derivative with respect to x of log base a of x. All right? That's the only thing we have left. Now, in order to do this, what we really want to look at is the change of base formula that we learned last year. I know I taught it to you guys. The O's taught it to you as well. And we may have said, you'll use this at some point next year, but you can probably forget it for right now. Well, now is the point that we use it. Log base a of x using the change of base formula is equal to ln of x over ln of a. That's just a hard fact. That is just true. Now when I look at this, I'm finding the derivative of ln of x over ln of a. Since a is just any number here, that's a constant multiple. This ends up being the same thing as 1 over ln of a times the derivative of ln of x. All I did there was pull the ln of a out in front of the derivative because it's a constant multiple. We just learned what the derivative of ln of x is. It's 1 over x. So this becomes 1 over ln of a times 1 over x, which we usually just summarize as in a big box down here. Last rule you're going to add to your sheet, the derivative of log base a of x is equal to 1 over x ln of a. Looks super difficult. Trust me, it's not that bad. It looks worse than it is. Did I get it right? Yeah, I got it right. Of course I got it right. There it is in a yellow box if you prefer that format. Again, add that to your rule sheet. It's the last one you get. All right. Here's a really difficult problem. There's a trick to it, but I'm not going to show you guys the trick. This problem involves log base a to the sine of x, all of the rules that we learned today pretty much. So we want to find dy dx. So dy dx is going to be equal to the derivative of a log base a is going to be 1 over the input. So 1 over a to the sine of x. A to the sine of x times the natural log of the base times the derivative of all that input. Derivative of a to the sine of x. We happen to have just learned that the derivative of a to anything is a to that anything, ln of the a. So this now is going to be 1 over a to the sine of x, ln of a, times a to the sine of x, ln of a, times the derivative of the input here, times the derivative of sine of x. Well, let's just look at some stuff that can cancel off here. I got a to the sine of x down here, a to the sine of x here. ln of a, ln of a. This whole nasty expression is just equal to the derivative of sine of x, which is equal to cosine of x. And that's such a simple problem to do. It would be even simpler if we had looked up here and we had recognized we have log base a and a to the bases match each other. So this is just going to be equal to sine of x. So the derivative of that function is just going to be equal to the derivative of sine, which is going to be equal to cosine. Again, this is trying to drive home that sometimes you have some tricks that you can make life easier for you. Skip that. Let's go here. If f of x is equal to ln of x minus 3, find f prime of x and state its domain. So what we're going to do here, take the derivative of ln of x minus 3. So f prime of x, again, we just learned that the derivative of ln is 1 over the input. So 1 over the input here being x minus 3 times the derivative of the input. So the derivative of the input would be 1. So multiply by 1, we get the derivative is 1 over x minus 3. Now we need to state the domain of this function. I'm going to do this the wrong way and then tell you why it is the wrong way. All right? So looking at this, if we looked at the domain of this function, we would notice that this derivative, we would notice that we have a fraction. So we know that we can't have a 0 in the denominator. So looking at this, I know that x cannot equal 3. So if I was to graph this derivative on my calculator, I would assume that I would only have no value at 3, right? So now what I'm going to do, I'm going to pull up my calculator, my handy dandy calculator, and I'm going to go into my y equals menu. Excuse me for 1 second while I restart my input device. And there it is. I'm going to calculate what is the derivative of ln of x minus 3, right? All right, so alpha window and derive d dx of ln of x minus 3 at x equals x. I graph it, and oh my goodness, that doesn't look right. I actually see on this graph that I don't have anything over here. Why would that be? Well, the reason why that is because if I go back to my y equals menu and I just graph the original function, ln of x minus 3, let's turn off this derivative. ln of x minus 3, there is nothing over here. The function is undefined. If the function is undefined, then the derivative is undefined as well. So what we have to do when we're identifying the domain of a function or of a derivative, we actually have to identify the domain of the original function. And I see an ln here. The domain for the original function means that x minus 3 has to be greater than 0. So the domain of the derivative is x is greater than, not 0, 3. So the big idea here is don't just go off of what the derivative says. Go back to the original function and identify the domain of the original function to find the domain of the derivative. This is really the first time that we've seen something happen like that. Now comes some fun. This is something called logarithmic differentiation. Like how we can differentiate something like y equals x to the x. Well, we have a rule when x is in our base. It's called the power rule. We have a rule when x is in our exponent. It's called the exponential rule. But we don't really have a rule where x is in both. So what we have to do in this situation, logarithmic differentiation, means take that function and apply a logarithm to both sides. So I've got ln of y is equal to ln of x to the x. As long as I do the same thing to both sides of the function, it's going to maintain equality. Now that doesn't look like it helps too much, except that the power property of natural logs allows me to take that exponent and put it down. I now have x ln of x. Now I've got ln of y is equal to x ln of x. Now I'm pretty sure I can take the derivative with respect to x of the left-hand side, as long as I do the exact same thing to the other side, d dx of the right-hand side. I'm going to maintain my equality. Well, the derivative of ln of y is going to be 1 over y times the derivative of y with respect to x. So 1 over y times dy dx. On the other side, I see I've got x ln of x. We know by now that we should use the product rule here in order to master this. So product rule, I've got the left x right derivative of ln of x, 1 over x, plus right ln of x, the left, 1. Looking at that, I'm running out of room, so I'm going to have to go back up here. I've got 1 over y dy dx is equal to 1 plus ln of x. Well, I want to find out what dy dx is. So now I've got dy dx multiplied by y on both sides is equal to y times the quantity of 1 plus ln of x. I don't want to leave y in my final problem, so I'm just going to take this. That's my y. I now have dy dx is equal to x to the x times the quantity of 1 plus ln of x. Whew! All right. That's fun. Now look at this problem down here. That's scary, isn't it? That looks like I'd have to use quotient rule. On top of quotient rule, I'd have to use product rule. On top of product rule, I would have to use rational exponents and chain rule, and rational exponents and chain rule as well. So that looks like way too much. So I'm going to show you a different way of doing it. I'm going to pause my video and set it up, and I'll be back in just 1 second. I bet you didn't even realize I was gone there. So I see y equals x square root of x squared plus 1 over x plus 1 to the 2/3 power. Well, this is on the logarithmic differentiation page, so I know it's going to be logarithmic differentiation. I will let you know if there's going to be a problem that you should use logarithmic differentiation on. And logarithmic differentiation, first step is to apply the natural log to both sides. So I've got ln of y is equal to ln of the quantity of x root x squared plus 1 over x plus 1 to the 2/3 power. All right. So now what I'm going to do, I'm going to try to expand this logarithm on the right-hand side using all of my logarithmic rules to make this a little bit easier. So I'm not doing anything to the left-hand side yet. But on the right-hand side, I see a product, I see a difference. I know products, when I expand my logarithms, can become addition. So this is going to become ln of x plus ln of the square root of x squared plus 1 minus ln of x plus 1 to the 2/3 power. Again, just using the product and the quotient rules for logarithms. Now I see some exponents here. I'm going to use the power rule for logarithms as well. Ln of y is going to be equal to ln of x plus square root is the power of 1/2. This will be half ln of x squared plus 1 minus 2/3 can come right down, 2/3 ln of x plus 1. Now I'm going to just differentiate the crap out of everything with respect to x. So I don't feel like rewriting that again. I'm just going to put d dx and d dx just to note to myself and take the derivative of the left and the right. Left-hand side, derivative of ln of y, that's easy. 1 over y dy dx. I'm going to warn you, this next part is a lot of writing. It's not difficult writing though, because here I've got the derivative of ln of x. 1 over x plus 1/2 times the derivative of x squared plus 1. That's going to be 1/2 times 1 over x squared plus 1 times the derivative of x squared, which is just going to be 2x. Again, using chain rule, because I have that x squared plus 1 in there. Minus 2/3 times 1 over x plus 1, technically times 1, because I've got a chain of x plus 1 in there. Now look at the right-hand side. It doesn't look as awful as what we originally started with. This would have just been a pain to use all the rules with. Last step for logarithmic differentiation, well, the penultimate step, I might say. I can cross off these 2's. I can now have dy dx. Just bring the y over the other side. Is going to be equal to y times quantity of 1 over x plus, bring that x in here, x over x squared plus 1 minus 2 over 3 times the quantity of x plus 1. And now really the last step is not a huge step at all. It's just rewrite the y value in there. So a lot of writing. Dy dx is equal to x root x squared plus 1 over x plus 1 to the 2/3 power times the quantity of 1 over x plus x over x squared plus 1 minus 2 over 3 times quantity of x plus 1. And that's logarithmic differentiation. It makes a complicated problem more palatable. Let's see here. Yep. And there's the practice problems. We'll go over these in class tomorrow. See you tomorrow.